All right. When you have a dual, I'm doing this because if I put it on YouTube, I can only do it in 11-minute increments. If you have a dual circuit, it means that the voltages are replaced by currents, current sources are replaced by voltage sources, resistances by conductances, capacitors by inductors. So there's like these, they're considered dual elements, and because the math, if you do that replacement, the math is the same. Anyway, so whether you're doing node voltage analysis or mesh current analysis, this little thing works. Do like the super Kaufmyn. So draw it, label it. So in this case, I'll be labeling node voltages. The third step has to do with dependent sources, and I'll show you, since we have a dependent source, I'll show you what you need to do with it. And then the fourth step has to do with if you have super nodes or super meshes, which unfortunately oh yeah, we do. We have a super, oh, but we're not doing mesh current analysis, darn. Well, I'll do mesh current analysis in the second part. And then the last step has to do with Kirchhoff. And so if you're doing node voltage analysis, you're going to do Kirchhoff's current law. If you're doing mesh current analysis, you're going to apply Kirchhoff's voltage law to all of the, well, I'll get there. So these 5 steps, you remember it, do like the super Kaufmyn. And why da instead of the? Anybody old enough to remember Willie Brown being the mayor of San Francisco? He was called the mayor. so it worked. Anyway, so I drew it. Okay, so that's step 1. Here it is drawn. It's got all of the things labeled. It looks great. Draw it neatly. 2, label the node voltages. Okay, so with node voltage analysis, we just pick a reference node. You know, I actually am going to draw this over because I like to draw it using what's called like a linear graph, which means that you don't have these corners and you collapse nodes into one point. It's kind of easier, I think. So I am going to do that. I just noticed a mistake on my own work, and that's why I'm hesitating, but I guess I can get around it. Okay, so this is node A here, right? And this is node B. I'm going to label this C and this D. Okay, so if I want, you know, if I just arbitrarily, I think I've got it right. Check my work here. Does this look like this? Yeah. Okay, so I'm going to label the node voltages now. I'm going to choose B as my reference, which means that VB is 0. Right? If I'm choosing the node B as my reference node, I'm going to label this voltage here at B, VB, because it's node B, and it's equal to 0. I put the A like this because I envisioned later that I wanted to actually label the voltage at that node. So it's the node voltage VA. Sorry, this is getting a little bit squeezed in. Let me put this up to find VOC. Okay, so this is VD. Here, let me see if I can kind of separate it from my, okay. And then this is node VC, and now I've labeled my node voltages. I've got the reference node, and then I've labeled all the other nodes. All right, so that's the second step. You know, I love keeping to-do lists and then crossing things off, so good. I've done that, check. So For the dependent part, you know, that third step, it's something to do with the dependent source. Here's what you have to do with it. You look at the controlling quantity of the dependent source, and you want to write that controlling quantity in terms of node voltages. Okay, because ultimately, and I forgot to ask this question, why do we want to use node voltage analysis or mesh current analysis? I mean, you know Kirchhoff's voltage laws and Kirchhoff's current laws. You could probably just solve the problem using those. So why go through this learning of these 5 steps?
More complicated circuits.
Yes, for more complicated circuits, for you to just kind of randomly say, okay, I'll maybe do Kirchhoff's current law here, Kirchhoff's voltage law here, and hopefully get enough equations and the right amount of unknowns and pray to the God of circuits that it all works out. This guarantees it. This guarantees